Now let us take a look at how this gradient boosting algorithm works for the classification problem intuitively. To understand the gradient boosting algorithm for classification, we are going to use this Titanic dataset. Here, this attribute is related to passenger class. It is a categorical feature. It has values like 3, 1, 2, and this is the age of the passenger, and this is the fare, passenger fare, and the last one is the survive. So this is the one refers to whether or not the person survived the crash. Here the one represents survived people, and zero is not survived. This dataset has independent attributes like age, gender, fare, P class with the target attribute as survived. Here, 1 denotes yes and 0 denotes no. Here we are going to predict the fare of the passengers on Titanic ship based on a few features like age, gender, and so on. So with this, we will understand the idea behind the gradient boosting, how it helps minimizing the error. As a first step, it fits the first model to this original data. Now, as we have done in regression technique in building the first tree, we have taken the average of our target attribute. Since this is a classification problem, it makes the initial predictions on the data by taking the log of the odds of the target feature. This is the target feature. This is usually the number of true values, values equal to 1, divided by the number of false values, values equal to 0. Here we have 4 true values and 2 false values are there um, in our target attribute. If you plug this in our formula, log log of 4 divided by 2. Here the 4 is survive and the 2 is not survive. As you all aware, in the case of log odds ratio, the numerator will have the probability of success and the denominator will have the probability of failure. So in this case, the ones are considered as true, hence the 4 trues are there divided by 2 false, and this gives us 0.7. So this is the first estimation of our target survived attribute. The easiest way to use log odds for classification is to convert a probability. Using this equation, we can convert the log odds as a probability. For this log odd value 0.7, the corresponding probability is 0.668. By plugging this log odds to this equation, e raised to the power 0.7 divided by 1 plus e raised to the power 0.7 gives us the probability. Here we have considered some of the assumptions like 0.5 as the threshold for classifying the yes condition and no condition. The value of probability is more than 0.5, it is yes, and below 0.5 as no, which is a standard one. Here in this chart, you can see that the light blue and the dark blue dots are the observed values. The dark blue dots are the passengers who did not survive the probability of 0, and the light blue dots are the passengers who survived with the probability of 1. The dotted line here represents the predicted probability, which is 0.7. Now we have the predicted value available here. So this the first estimation of the target attribute survived is 0.7 is the log odds. The same value is used as a predicted value for all the observations. With this predicted value, we can find out the residual. The next step is we need to find the residual. How do you find out the residual? The actual value minus the predicted value. Here 0 minus 0.7 is negative 0.7, and the 1 minus 0.7 is 0.3, and 1 minus 0.7 is 0.3, and so on. With this residual in place, now gradient boosting creates another model in sequence. So, which is a second model, it is a weak learner. So this one will be created in sequential to predict the residuals. In this case, the independent variables are P class, age, gender, and so on. But the dependent variable is residual, not survive. It may seem upset that we are considering the residual as a target variable. So this is how it works. As we move further, you will understand why it considers the residual as a dependent variable. The idea here is the second model predicts the error or the residual. Please take note that we are restricting the number of leaves that we will allow in the tree exactly as we did when we used gradient boost for regression. To make this simple, we are limiting the number of leaves to 3, but in reality, it is common to allow anywhere from 8 to 32. Because of the limit on the leaves, one leaf can have multiple values in it. So in this case, you can see that in this leaf, 2 residuals landed in here. So if you see the condition here, P class, passenger class is not equal to 2, and age is greater than 30. And look here, we have only 2 records, which has age is greater than 30. And for this 38 to 0.3 is the residual, and for this the residual is 0.3. These 2 values landed in a single leaf. And similarly, here we could see that 3 values landed in a single leaf because of the limitation of the leaves. Here, the prediction are in terms of log odds, but these leaves are derived from probability, which can cause some kind of disparity. Hence, we need to calculate the output for each node, each leaf node. We can't simply add the values like how we did it in the gradient boosting for regression. So there is a formula for this to transform these values. Here, the predictions are in terms of log odds, whereas here we have in the leaf we have the values in terms of probability. So in this case, what we are doing is we are using an equation like this sum of residual. So in this case, the numerator in this equation is the sum of residuals in that particularly divided by the denominator, the sum of previous prediction probability for each residual multiplied by 1 minus same previous prediction probability. This is because why we are transforming each leaf value using this equation is the predictions are in terms of the log of the odds, and this leaf is derived from the probability. So we can't add them together and get a new log of the odds prediction without some sort of transformation. For that reason, it requires transformation. So in this case, the first leaf has only one residual value, that is 0.3. And since this is the first tree, the previous probability will be the value from the initial leaf. Thus, same for all the residuals. So if you plug in the value 0.3, since we have only one value here, residual is, we don't have to sum it, 0.3 divided by the previous probability, the first leaf probability, 0.7 into 1 minus 3, so 0.7 minus 0.7. This gives us 1.43. This is the output value for this tree. Similarly, if you plug in these values into this equation, we can get the output for each leaf. And if I plug in the values here, if I put the values here, you can understand this 4.29 is the output for this leaf, and this is the output for this leaf, and this is the output for this leaf. Now we can find out the log of the odds prediction with this equation. So the new prediction is base log odds. For the sake of simplicity, I have just taken only 2 observations here, the second one and third one. And this one, the base log odds plus learning rate into predicted residual value. So what is the base log odds? For the base models, the first models, uh, the log odds was 0.7 plus 0.8. In this case, I have considered the learning rate as 0.8 multiplied by this one. I have taken this one first, 4.29. This is the log odds. And if you do the math, it gives you 4.132. This is the log odds of the prediction for this passenger. Okay, and if you convert this to into a probability, you'll get 0.805. So the new predicted value is 0.805. And if you subtract this value from the actual value, you get 0.195. This is the new residual. The new predicted value now is 0.805 and the new residual is 0.195. This new predicted value is somewhat close to this one. And if you compare the residuals, if you compare the residuals here and this one is 0.3, the base model residual, and the new weak learners, the second models residual 0.1. And with this, we can see that there is a drop in the residual. It's a good sign. Similarly, now if you take a look, if you plug in this value here, 0.7 was the base log odds plus 0. Is the learning rate into 1.43. You get the log odds 1.8. If you convert this into probably 0.648, 0.648, but this is it's a very less. It's not that good. The residual is slightly more than the actual, the first residual. Okay, we don't see a drop here. Instead, there is a slight increase here. But this is very unfortunate. But by building more trees, it can come down. The error will come down. So now we have the new predicted value and we have the new residual. With this new residual in place, it builds another tree in sequence. This is the another tree. So the previous one, the error was residual was 0.19 for this record, and for this observation 0.352 here. Just example sake, of a simple sake, I just took only these two observations. I did not take into account of this one. Okay, and here if you do the math, so you need to do the transformation. When you do the transformation using this equation, you get the log odds for each corresponding leaf. In this case, when we did the transformation using sum of residual divided by probability into 1 minus probability, previous probability. So when I plugged in, this value, this is the logs. When you plug in these values here, look here. Now we can find out the log of the odds prediction. Here, the base log odds is 0.7. In this case, it combines three trees: the base model, and then the previous model, and the current model. So 0.7 plus 0.8 is a learning rate. I have considered the 0.8 as a learning rate here. And here the log odds is 4.29. Okay, 0.352. Okay, sorry, you need to look here. 0.8 into 1.43, look at this way, plus 0.8 into 1.391, so 2.95, 0.74. Yes, this is the one, the previous model. 0.8 is the learning rate, and 4.29 is the previous, previous weak learners, log odds, plus the current one, 0.8 into 1.428. It gives us the log odds as 5.274. To convert this one, the probability is 0.840. And the new prediction for passenger class 2 here. For this, we can see an improvement here, 0.74. So this is the new prediction. And with this new prediction value, we can see that 1 minus 0.840, we get 0.16. So now the residual got reduced further. If you look at this record, the second iteration, the residual was 0.19, and in the third iteration, the residual is 0.16. With this, we are able to understand in each iteration, the residual value is going down, it's dropping. And similarly here, see earlier it was the 0.352, and now it is it got reduced. Now for simplicity's sake, we will take only this record. Or yeah, so if we take that record, we can see that the first iteration, the residual was 0.3, and the second iteration, it was 0.19, and the third iteration, there is a drop in the residual. You could see a good sign. The new predicted value was 0.805 in the second model. In the third model, the predicted new predicted value is 0.840. So now we just repeat the same process over and over again, building a new tree, making predictions and calculating residuals at each iteration. We could see that each iteration, there is an improvement in the predicted value. And also we could see a drop in the residuals. So we do this until the residuals are super small or we reach the maximum number of iterations we set for our algorithm. With this, we are able to understand it started with the base model and iteratively created the weak learners in sequence. And in each iteration, we can see that the residual values are dropping. It's all because of combining all the weak learners resulted in a strong model, which resulted in reduction in residual. So initially it was 0.3, 0.19, and 0.16. Hope you understood how the gradient boosting for classification works behind the scene.